Hi, wishing you all. I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the eigenvalues of energies and then eigenwave functions. So, in the previous session, we have discussed about the uh, Schrodinger's time-independent equations and then particle in one-dimensional infinite potential variables. We can call it as particle in one-dimensional potential well or infinite potential well. Okay, so in there we have seen that if the particle is inside the potential box, what is its wave function, and then so if the box is in that one-dimensional potential box or else infinite potential well, what is the eigen energies? Now we are going to see that. So already we have seen the wave function of a particle which have the potential energy uniform inside the potential box, and outside it has infinite potential energy. So there, in that case, what is the wave function we have seen by taking the Schrodinger's wave equation, which is for one dimensional case. So this is the regions, this is the previous session topic. Particle in one dimensional potential box. So here we have taken that inside the potential box, the potential energy of the particle is zero. So where inside means that the region will become 0 is less than equals to x, less than equals to a. But when outside, the potential energy is infinity. So that we are calling as infinite potential well. So where the potential energy is infinity, so the region x is less than 0 or x is greater than 0 outside the potential box. So then we have taken that Schrodinger's wave equations for one dimensional case. So dou square psi by dou x square plus 2m into e minus v by h cross square into psi is equals to 0. So in this case, the potential, if we take the inside the potential box, so the potential energy is uniform. So the potential energy is uniform inside the potential well. So that inside v is equals to 0. Where is the case of, in the case of 0 is less than x, less than a. So in this case, v is 0. So that when v is equals to 0, we got the expression, and then dou square psi by dou x square plus k square psi is equals to 0, where we have taken 2mv by h cross square as k square. So the solution for this first equation, psi of x is equals to a sin kx plus b cos kx. Okay, when substituting the first boundary condition and second boundary condition, so we got the solutions for that. When applying first boundary condition, that is x is equals to 0, then we got b is equals to 0. So applying the second boundary condition, x is equals to 0. Okay, as the boundaries are x, because the potential box width is a, so 0 to a. So that the first boundary condition is x is equals to 0. So there, in that case, when substituting x is equals to 0 in this second expression, so we got b is equals to 0. By applying the second boundary condition, x is equals to a. So we'll get the value of 0 is equals to a sin k. 0 is equals to a sin k. So here either a may be 0 or sin ka may be 0. So but a is not equals to 0. A is not equal to 0. If a is equals to 0, psi becomes 0, so that there will be no solution. Okay, so means that the particle is not in the well. So that we are taking sin Ka is equals to 0. So that implies K, we got K is equals to n pi by A. K is equals to n pi by A, but here n is equals to 1, 2, 3 and so on, but not 0. So if n is equals to 0, then the energy becomes 0. So when energy becomes 0, psi of x becomes 0. So if psi of x becomes 0, that is if the energy is 0, it couldn't be exist. So the particle couldn't be exist with 0 energy inside the potential box. So that particle with zero energy cannot be present in the box. That is, particle in the box cannot have zero energy. So finally we got the wave function for the motion of the particle which is inside the potential box region of 0 is less than x less than a. So simplifying, we got the wave function for the particle which is in motion. So sin of x is equals to a sin kx. So where k is equals to, as we derived, n pi by a. So substituting n pi by a instead of k. So the final expression for the wave function of a particle moving inside the potential box, sin of x is equals to a sin n pi a x. Or else sin of x is equals to a sin n by x by a. So this is the wave function for the motion of the particle in the region of 0 is less than x less than a. Okay, so now this is the wave function of the particle inside the potential. So now we are going to see the energies of the particle, the energy of the particle, that is wave associated with a particle. So when it is moving inside the potential box, what is the energy values, how the energy values will be changes. So eigen values of energy. So we know that k square is equals to 2me by h cross square. So just now, because we recall the previous session's topic, so there we have seen k square is equals to 2me by h cross square. So from here, the energy is equals to, that is k square is equal to 2me by h cross square. So as we want energy E value, so that k square h cross square is equals to 2me. So that implies k square h cross square by 2m is equals to E. So that as we want E energy value, so that I'm taking 2m to the other side. So we got E is equals to k square h cross square by 2m. Okay, so now we have to substitute the k value. So k value is the root of 2m e by 2m e by h cross square, but actually the k is equals to n pi by a, k value n pi by a. So k e is equals to k square h cross square by 2m. K is n pi by a. So k square is equals to n pi by a square. So k square is equals to n square pi square by a square. So k square be substituted in this expression. So we get E is equals to n square pi square by a square into h cross square by 2m. So simplifying this, n square pi square by a square into h square by 8 pi square m. How we get E is equals to k square h cross square by 2m Substituting K is equals to N pi by A. So E is equals to, this implies what is for K is K square. K square is equals to here. K square is equals to 2ME by H cross square. From this, E is equals to K square H cross square by 2M. So substituting K is equals to N pi by 8 implies K square is equals to N square pi square by A square. So E is equals to N square pi square by A square H cross square divided by 2M. So it is equals to N square pi square H cross square by 2MA. 2MA. So here taking as H cross is equals to H by 2 pi. H cross is equals to H by 2 pi. So substituting here instead of H cross, H by 2 pi. So E is equals to N square pi square by 2MA to H by 2 pi square. So E is equals to N square pi square H square by 4 pi square divided by 2MA. So that N square pi square H square by 4 pi square into 2MA. So N square pi square H square divided by 8 pi square MA. So pi square gets cancelled. So A is equals to N square H square by 8MA. So which we got here. En is equals to N square H square by 8MA square. So here A square, N square pi square by A square, no? So I forget to write a square. 2MA square here also. So here N square pi square by A square into H cross square divided by 2M. So N square pi square H cross square divided by 2MA square. So substituting H cross is equals to H by 2 pi. So we got E is equals to N square pi square into H by 2 pi whole square divided by 2MA square. So when simplifying this, E is equals to N square pi square into H square by 4 pi square divided by 2MA square. So it is equals to N square pi square H square by 8 pi square MA square. So that finally we got the energy expression E is equal to N square pi square by 8MA square. So from this equation, it is clear that the lowest energy of the particle is obtained by putting n is equals to 0. N is equals to 1. So if n is equals to 0, what happens? Zero energy. We'll get zero energy. So zero energy cannot be exist inside the potential box, so that n is not equals to 0, so that the lowest energy of the particle can be obtained by putting n is equals to 0. That's why we say that n is equals to 1, 2, 3 and so on. So when taking up n is equals to 1, when n is equals to 1, so E1 is equals to h square by 8m a square. So that is En is equals to n square h square by 8m a square. This is the energy, eigen energy of a particle. So En is equals to n square h square by 8m a square. So when substituting En is equals to 1, E1 is equals to 1 square h square by 8m a square. So that E1 is equals to h square by 8m a square. Okay, so this is known as 0 point energy of the system. This is known as 0 point energy of the system. So for n is equals to 1, 2, 3, we get energy values of the particle in the potential box. So E1 is equals to h square by 8ma square. E2 is equals to 2 square. N square means n is 2. So that substituting instead of n, 2. So E2 is equals to 2 square h square by 8ma square. So that we'll get 4h square by 8ma square. So E2 is equals to 2 square means 4 h square by 8ma square. So this can be written as 4E1, as what is the value of E1 we got here when n is equals to 1. So E1 is equals to h square by this one, h square by 8ma square. So we can write instead of h square by 8ma square E1. So as like that, E3 is equals to 3 square h square by 8ma square. So implies E3 is equals to 3 3 is 9. So h square by 8ma square is same as E1. So E1, 9 E1. So we can write commonly En is equals to n square E1. Also, we can write the energies for different values. En is equals to n square E1. En is equals to n square E1. So the spacing between the nth energy values, nth energy level, and the next higher level increases as n plus 1 whole square E1 minus n square E1 is equals to 2n plus 1 to E1. So like this, the space between the energy levels going to higher energy levels. So that is when En is equals to 1, E1 is equals to h square by 8m a square. E2 is equals to 4 E1. E3 is equal to 9 E1. So likewise it is going. So here what happens, h square, that is E1. So 4 E1, 9 E1. So means that the spacing between the nth energy level and the next higher energy level increases. So how it can be increased? So the spacing. So E1, E2, E3, E4. So comparing to the spacing between two energy levels, so to the other one. So this one is increased. The spacing between the energy levels to the next higher energy level increases. So likewise, the spacing between the energy levels B for a particle which is moving inside the potential box. So these values of En are known as eigenvalues of energy. So these values of En are known as eigenvalues of energy, and the corresponding wave function psi n as eigen functions of the particle. So the integer n is quantum number of energy level En. So En is known as eigenvalues of energy, and psi n, the corresponding wave function psi n, is called as a eigen wave function of the particle. So n is the quantum number of the energy level En. So now we see that eigen wave functions. Now we shall see the eigen wave functions. So here the eigen wave function for the motion of the particle, as we derived from the by taking the Schrodinger's one-dimensional case. So we got psi n of x is equals to a sine n pi x by a. So where in the case of 0 is less than x less than a. So psi n of x is equals to 0 in the region x is less than equals to 0 and x is greater than equals to a. So the total probability of the particle, so that the particle is somewhere in the box, must be unity. So integral 0 to a. So that is the dimensions of the potential box width is 0 to a. So that integral 0 to a, the probability px dx is equals to integral 0 to a 0 to integral 0 to a modulus I n square dx is equals to 1. So what is the p of x? So a square sine square n pi x by a. So substituting that p of x, so the probability density of your particle for a small distance is p of x. Okay, so this also we have seen in the previous session. So p of x is equals to a square sine square n pi x by a. So integral 0 to a square sine square n pi x by a dx is equals to 1. So as a is constant, so a square integral 0 to a 1 by 2 1 minus cos 2 by n x by a dx is equals to 1. So now applying the now taking that a square by 2 into x minus a by 2n pi sine 2n pi x by a, limit 0 to a is equals to 1. So integrating, we got this value. So the second term becomes 0 at both the limits. So this term becomes 0 at both the limits, so that we are taking a square by 2 into a is equals to 1. So that a square a by 2 is equals to 1. So what is the value of a? So a square a is equals to 2. So a square is equals to 2 by a. A is equals to root 2 by a. So this is the a value. So the normalized wave function is substituting a value psi n is equals to a sine n pi x by a. So in this, substituting this a value. Okay, in this value eigen wave function, we are substituting this a value. So a is root 2 by a. So psi n is equals to a value is 2 by a sine n pi x by a. So This is the normalized wave function. Psi n is equals to root 2 by a sine n by x by a. So the wave function psi 1 has two nodes. The wave function psi 1 has two nodes. One is at x is equals to 0. Other one is at x is equals to a. When taking psi 2, psi 2 has three nodes. One is at x is equals to 0, another one x is equals to a by 2, and x is equals to a. Another one x is equals to a. When psi 3 has four nodes. One is at x is equals to 0, x is equals to a by 3, x is equals to 2a by 3, and then x is equals to a. So that the nodes of psi n has n plus 1. So the wave function has n plus 1 nodes. Thus, psi n has n plus 1 nodes. So here, this is the way the potential box 0 to x is equals to 0 to x is equals to a. So this is the wave functions. So psi 1, psi 1, psi 2, psi 3. That is, this is psi n of x. Psi n of x. Okay. So here we are getting that nodes. So when psi 1, it has two nodes. So psi 1 has two nodes. And psi 2 has here three nodes. And psi 3 has four nodes. So 1, 2, 3, and 4. So here 1 and 2. Here 1, 2, 3. So when psi 1 we are getting at x is equals to 0, one node, and x is equals to a other. Okay. Likewise, it has n plus 1 nodes. N plus 1 nodes. So psi of x has n plus 1 nodes. So psi n has n plus 1 nodes. Now we see the probability of the location of the particle. Probability of the location of the particle. So the probability of finding a particle over a small distance, which is at dx at x, is given by p of x dx is equals to modulus psi n square dx. So p of x dx is equals to 2 by a sine square n by x by a dx. So the probability density for one dimensional motion is p of x is equals to 2 by a sine square n by x by a. So the probability density is maximum when n by x by a is equals to pi by 2, 3 pi by 2, 5 pi by 2, and so on. So x is equals to, in this case, a by 2n, 3a by 2n, 5a by 2n. So now for n is equals to for n is equals to 1, because n is equals to 0 does not exist. So taking as n is equals to 1. So the most probable position of the particle is at x is equals to a by 2. X is equals to a by 2. For n is equals to 2, the most probable position of the particle is at x is equals to a by 4, and then x is equals to 3a by 4. For n is equals to 3, the most probable position of the particle is at x is equals to a by 6, x is equals to 3a by 6, x is equals to 5a by 6. So thus the wave functions and the probability density functions for the particle in one dimensions are varying likewise. So psi 1 of x is equals to root 2a by root 2 by a sine pi x by a and the probability density of finding the particle P1 of x dx is equals to psi 1 modulus psi 1 of x square that is equals to 2 by a sine square by x by a. So when taking psi 2 of x, we'll get root 2 by a sine 2 by x by a. So P2 of x dx is 2 by a sine square 2 by x by a. So taking as psi 3 of x, that is equals to root 2 by a sine 3 by x by a. Then probability density P3 of x dx is equals to 2 by a sine square 3 by x by a. Likewise, the wave functions will be varied. So the energy values, we know that for a particle in potential box, the energy of the particle is En is equals to n square h square by 8m a square, where n is equals to 1, 2, 3 and so on. So in this relation, the n is the Planck's constant and m is the mass of the particle and a is the width of the potential box. So for discrete values of n, we have discrete energy levels. These energies are quantized. And these energies can be represented by discrete energy levels within the box. For higher energy values, the separation between the energy levels increases. The probability of occupation of these energy levels is given by the Fermi-Dirac distribution. The occupation of the particle in the energy levels. That is, the probability of occupation of these energy levels is given by the law of Fermi-Dirac distribution. So here this is of psi value and this is of psi modulus psi square values function. So that here we can see that. So here the eigen wave function. So here En is equals to n square h square by 8m a square. So the wave functions and the corresponding probabilities and energy levels of the particles are seen by this diagram. Okay, so this is of probability density. This figure shows that the wave functions of the particle associated with a wave which is in the potential box. And this second figure shows the probability density of a particle within that wave in the potential. So the number of nodes increases with increasing energy and also the energy of the particle becomes greater. So the quantum mechanical model breaks down. As the energy levels get closer together, overlap, it forms as a continuum. And this means particle is free and can have any energy value. At such high energies, the classical mechanical model is applied as the particle behaves more like a continuous wave. So therefore, particle in a box problem is an example of wave particle duality. So this is about the eigen values of energies, eigen wave functions, and then we found that we derived expressions for the probability of finding the particle, probability of location of the particle which is in the potential box. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.